waveform, and I put up a bunch of stuff on. I didn't require any homework, but I put up a bunch of reading. How many at least looked at it? If you did look at it, you realize a lot of the stuff we're going for is to find a nice, neat, condensed way to analyze any kind of a pulsed waveform. So let me get back to what I'm doing. This you'll be responsible for on Friday. So, I mean, not this particular thing, but I'll tell you what. So we started off, and this is just a rehash of what we've been doing, where we had this. We had a waveform that went, I don't know, somebody's having fun with me, or just the way things are. We had a waveform that did this. And it was repetitive, so it was doing this. And this is in time. The height of this I had as A. The on time is tau. Right here, we're calling the rise time equal to the fall time. So we're going to just call them both T rise. And in the real world, they find the shortest one and use that. And then we said that's periodic, and the period is T. And then we said, first of all, it's periodic, and I went through and I did a couple of derivatives. Do you all remember that class? Then I said, well, this entire thing, because it is periodic, can be represented by this series. X of t is equal to a summation from n equal minus infinity to infinity of c of n e to the j n omega naught t. And omega naught really is 2 pi over the period t. Or said better, you could just say that f naught is 1 over the period, and omega naught is 2 pi times f naught. That's probably the way you're used to saying it. Then we were talking about Cn right there. Now that's what I was getting at when I did that double derivative thing, so I could easily get that value. So we found that C of n for this exponential series is equal to a times tau over t. And do you all remember that exponential series I had there, right? And I was condensing it into a couple of signs. You all remember that, class? So let me go through and actually, let me do it this way. After I was doing all that thing, all that stuff, what we ended up with was, no, I'll do it this way. It was a tau over t, and then we had that, remember the 1 minus e to the minus j n omega naught tau rise minus e to the minus j omega naught tau, and then plus e. Do you all remember that and how I turned it into a factorial, or two factors where I had 1 minus e to the minus j omega. If you look in your notes, you've got your notes right there. I've turned that into a couple of 1 minus e to the minus j omega tau rise. I had this as, put it here. I had 1 minus e to the minus j n omega naught tau rise minus e to the minus j n omega naught tau, and then plus e to the j minus j n omega naught quantity tau plus tau rise. Do you all remember that? And I turned that thing into 1 minus e to the minus j n omega naught tau rise. And then I had this as 1 minus e to the minus j n omega naught tau, right? I said that, and then I factored in e to the minus j n omega naught. This is the thing I wanted to get at today. I'll just go this way, because you should have that in your notes. I factored in e to the minus j n omega naught tau rise over 2 out. Then I had e to the j n omega naught tau rise over 2 minus e to the minus j n omega naught tau rise over 2 here. And for this one, I factored the same thing only with tau, and I had e to the minus j n omega naught tau over 2 out front, and then that brings it as e to the j n omega naught tau over 2 minus e to the minus j n omega naught tau over 2. All that said, I'm just kind of rehashing what I did last time for that. This and this, I turn into 2j sine of that exponential argument. Do you all remember that? That's where I was going. I'm trying to lead you there, just refresh your memory a little, because this is how we got there. Now, do you all have that in your notes class? You said? Okay. So, right here, after we do that sine business, where that's a sine and that's a sine, I put this in the notes, I'm trying to save time. After we do that, we end up with e, this is going to be this same thing here. We have e to the minus j n omega naught, and then it's going to be tau plus tau rise over 2. And then it's going to be times 2j squared times the sine of n omega naught tau over 2 times the sine of n omega naught tau over 2. And I hope you can appreciate what I'm trying to do is just take that and say that's what it will be if we replace the exponentials with sines. Do y'all agree with this class right here? So I take this and I stick it over here. So now I have e to the minus j n omega naught tau plus tau rise over 2. That's a phase term. I have sine of n omega naught tau rise over 2 sine of n omega naught tau over 2. And if you remember what went on down here, there was actually an a over tau in front of there, but then there's going to be terms of the order, and I forgot one thing, j2 squared. I'm going to have jn omega naught squared downstairs here, and I actually had an a over tau here, right there. I just want to explain something because I want to get to the bottom line here, but I'm going to tell you, after all is said and done, if you look at your notes where we left off, I'm trying to just make you aware of how I get these signs right here, but this is the key thing, what I'm about to show you. Now you see there's a j squared here and a j squared there on top. Y'all with me on this? That gets gone, which is nice. Now the next thing, there's a 2 squared there. Now what I really want to do is I want to turn these into sinc functions. And remember that the sine, or the sinc of x, sinc of x is really the sine of x over x. You with me on this class? So the goal is to have the same arguments for the sine function here as down here so we can turn it into a sinc function. Y'all with me? So I'm going to take this n omega naught squared, I'll separate it, right? Now, this was a t rise, sorry about that. That was a over t rise when we did the double derivative. So what I'm going to do is take this t rise and put it in this one. And you see how you have that 2 squared here? So I'm going to divide top and bottom by one of those 2's here, then another of those 2's here. I'm going to turn them into sinc functions is what I'm telling you. And I just want you to see how it's done. This one has got tau in it, so I get tau down here, and I have to multiply this by tau. And that tau rise is going to come down here, actually. let me just explain exactly what I'm trying to do. I'm trying to fit the form of sine x over x. The arguments of those sine functions have to appear in the denominator for me to turn this into sinc functions, all right? And we're going to see in a second that all this kind of smooths itself out and becomes something very simple to understand. But for now, at least appreciate, I'm trying to show you this. In the notes sorry. That's on me. My bad. Anyway, I want you to just appreciate that right now, this is how you get where you're going. It's in the notes exact. All right, but this is from last time. So here, if you look at this, I've got sine of that argument appears down here, then I have sine of that argument appears down here. You with me? So it's a sinc function. This is the part you write down. That means that value of C of n is actually A over tau divided by capital T. Tau, again, is the on time, and T is the period. What do you call the on time divided by the total period? There's a word that you have in digital all the time. The duty cycle. Do y'all remember that? Duty time or duty cycle, right? It's the percentage of time the waveform is high, usually, is on. So this is the duty cycle, which is nice. Then you're going to have the sinc of, first one, n omega naught, and it's going to be tau rise over 2. Then it's the sinc of n omega naught tau over 2. And that's what C of n is. Still, in your mind, if you don't appreciate it, I understand, but you're going to get used to this stuff, because by the time you get in your senior courses, you're going to get inundated with this all the time. Go ahead.
The E term is still in there as well. Right?
Yeah, the phase term I'm going to put in right now. All right. This is just the magnitude, and you have to understand, this is the thing you really care about. There will be the phase term also, the e to the minus jn omega naught times tau plus tau rise over 2. You don't have to worry about that phase. It does affect things, but for now, when we look at spectrums, we're worried about magnitude. I'm just telling you. This is going to be the value of C of n that goes in this series. Something I didn't tell you, but because I used the derivative method to get the value of Cn, there's one value of C of n that is not something that comes out of this term. Can you guess what it is? Think about when you all did Fourier analysis, right? Fourier series analysis. Do y'all remember the average value was called C0? Do y'all remember that? The average value is what? It was the equivalent DC value. You integrated the function, whatever it was, over a period, and you divided by the length of the period to find the average value. Do y'all remember that? So write this down. This is true for n unequal to 0. C0 is just 1 over the period. The integral from minus t over 2 to t over 2 of simply, and should call this v of t right here. V of t dt. You would have e to the minus jn, but n would be 0, so e to the 0 is just 1. It's just that's the average value of the signal, C0. I think you remember that. Okay. I have this stuff, and this looks foreign and scary. Why are we doing it? It's a good question. And you're going to see. Now I'm going to take this series, this double exponential series, with these as the coefficients, and I'm going to make something useful of it. I'm going to show you how this thing can be turned into a cosine series. And the reason the cosine series is so important is if you think about when you do circuit analysis for a given constant frequency, you assume the input signal is some what? Some magnitude, like V naught cosine of omega t plus a phase angle, right? Well, that omega can be anything. And you would do it in a phasor domain, right? You would take that V naught cosine of omega t plus phase angle, make it just V naught at an angle, theta, correct, class? you're gonna see we'll be turning this into a cosine series, and every one of those terms can be looked like the phasor input to a circuit at a given frequency. So, coming back here, now it gets interesting. And I put this in the actual notes that I added, but some of you, if you didn't look at it carefully, you probably missed this. So now what I'm gonna do is take that series, we got the Cn for that series, and I say x of t is equal to, go out, let me get this. I'll just put the whole thing, and I'll show you how you get it. This is gonna be equal to the summation of C of n e to the j n omega naught t, n equals minus infinity to infinity. And now, you don't have to write this down, it's in the notes, but at least appreciate what I'm doing. Now I'm gonna take this and break it into two series. I'm gonna say this is really a series, n equals minus infinity, all right, to 0, or to 1, to n equals minus 1, of C of n, actually, yeah, minus 1, C of n, e to the minus j n, or I mean plus j n omega naught t, plus C0 plus the summation from n equal 1 to infinity of C of n e to the j n omega naught t here. So, go ahead.
Oh, sorry.
What I'm really trying to tell you is I just took this series and I took the negative n terms here, the positive n terms here, and there's C0 here. What I'm actually going to do to make it a little easier to see, I'm going to put C0 out here. Just shift the position of that. Now, when you look at this, there's something really interesting that happens. When I have anything, like if I have, if you take a look at C of n itself, C of n can be written as magnitude of C of n e to the j angle of C of n. Do you all agree with that, class? Magnitude and angle. If you talk about C of n conjugated, still it's magnitude of C of n, then it would be e to the j, and it would be minus j angle of C of n, right? Y'all remember that? The only thing you're doing is basically changing the sign on the angular term when you do a conjugate. I want you to keep that in mind. So when I take a look at this right here, I'm going to write this in terms of magnitude and angle. This itself looks like the summation n equals minus infinity to n equals minus 1, magnitude C of n, right? And then it's going to be e to the minus, or I'm sorry, e to the plus j angle of C of n here, and it's going to be times e to the j n omega naught t. And what I can do is add, I could actually just create one term right there, so I can, just one term in the exponential. Right there. Plus the summation from n equal 1 to infinity, magnitude of C of n, e to the j n omega naught t, right here, plus the phase angle of C of n here, and then plus C0. Now I just did this for, can anybody guess the next steps? If you looked, you know it. Remember, anytime you see these exponential terms like that, e to the plus and minus j business, always think trig in the back of your mind. Now, here's the deal. See this negative sign? That's for the values of n, right? I want you to watch this part right here because it's important to appreciate. In your 400 level courses, you're probably gonna see this kind of stuff happen all the time. What if we make it positive? Then anywhere there's an n, you have to put a minus n, right? So make that minus n, that doesn't change, right? Minus n. When that becomes minus, right? Now remember what I said with conjugation, if you have like a minus, or a plus jb, the conjugate of that is simply a minus jb, and for the phase angle I did it here. So what's actually gonna happen is, this will become minus, and this angle will be minus as well. So I can make that minus there. This will stay the same. Y'all follow me on this, class? That when you have if you sum, remember before it was minus infinity to minus 1. And, well, suppose we make it 1 to infinity, and where the n is, we put a minus sign. We also have to conjugate the angle. Are you with me on that? And then when we do that, what actually happens then? What do you see this becoming? Anyone? Let me ask you, doesn't this look like e to the j angle plus e to the j angle? That c of n is the same in both, right? What is that? What is e to the j theta plus e to the minus j theta equal to? If I put it over 2, it's what? It's cosine of theta. Do y'all remember that, guys? How many do? These are Eulers, and Eulers are so important for engineers. There's the sine, the cosine, and then there's the exponential identity where you have e to the j theta is cosine theta plus j sine theta, right? So here, now I can say this, I call it x of t, it's really v of t, it's my signal. Now I can say that v of t itself can be rewritten as this, c0 plus 2, right? Now I can just put a single summation down here, n equals 1 to infinity of 2 magnitude of c of n. This is the important one, write this down, right here. This is one of the important ones. Then it's going to be times cosine of n omega naught t plus the phase angle of c of n. Now here's why that's so important. You've got c of n right here. Right there. You have it. When you take a look at these terms, it looks like it's a mess. There's so much going on. But we're going to take this and approximate. N omega naught is really going to become just omega. And we're going to take a look at how this thing behaves versus frequency and get what's called an envelope. Y'all heard the term envelope of like an FM wave or an AM wave, right? Y'all remember that? It's just where the peaks occur if it's a sinusoidal function that's varying at a high speed. We're going to get the envelope of this, and you're going to see how this stuff is going to just become very easy to understand. But this is real important right here. Because when you have a circuit that's a linear time invariant circuit made of capacitors, inductors, resistors, and stuff like this, each one of these terms is really a phasor value at an angle for a given frequency, and you can analyze circuits term by term that way. I'll get to that later, but I want to make sure you understand this. Now, here comes some, this is the really EMC analysis. And it's the part that I got to tell you, I have to go through problems with to make you appreciate it, but let's see if that so if you look here, right, and I put the CN, I put it up here, I'll do it again. CN was A over tau over T, and then it was times the sinc of omega tau, or n omega naught, pardon me, over 2, call that T rise, times the sink of n omega naught tau over 2, and times the phase term you're not going to worry about the phase term. That's what that C of n is. Now here's what we're going to do at this point. If you look at this, and I'm just going to try to make you appreciate this. I'm not going to test you on this, but try to appreciate this. These are values for different frequencies, all right? N omega naught are specific frequencies. So if we were to look at just, we'll take magnitude of C of n here versus omega this way. And usually you'd be in a logarithmic axis. What you would get for it, it would be like omega naught, 2 omega naught, 3 omega naught, and so forth, all the way up the line. You're going to have values for this. Something like this. It'll keep going. And then at some point, it's going to start coming down. And at another point, it's going to come down faster. But just appreciate that. Here, n omega naught would be plotted on the omega axis, and there'd be spikes. Do y'all follow me on that? Because they have singular values, only at those frequencies. But when we do EMC analysis, what we take a look at is the worst case analysis. This is real EMC analysis. We simply we're going to take this thing, instead of n omega naught, we're going to replace that with omega. We're going to see what this thing looks like in a spectral plot. This would be worst case. Then you'll understand why we're doing it, especially when I do a few problems. Then it'll make sense. The math sometimes gets a little overwhelming. So when I take a look at this, here's what happens. First, it's this. I'm going to let omega become n omega naught. That's the first step. Y'all with me? So now it's a continuous frequency, and we want the envelope of the signal. So from here on, we're talking about the envelope. And then we're going to say f would be equal to omega over 2 pi. So then we're going to plot it versus f. So let me go here. I'm going to first take C of n right here. I'm going to, anywhere there's an n omega naught, I'm going to put omega in. With me? And then here. It's a little messy, but y'all follow what I've done and why I've done it? Then anywhere there's omega, all right, I'm going to replace it by 2 pi f, right here. So I'll say this. I'll say I'll replace omega by 2 pi f, right here. And then I'm going to get this. I have C of n here equal to a tau over t. And then it's going to be the sink here of omega tau rise over 2. Well, omega is replaced by 2 pi f, so this becomes pi times tau rise times f. And then the next one is the sink of pi tau times f. And then finally, you're going to have e to the minus j 2 pi, or I'm sorry, pi f times tau plus tau rise. The phase term, the n term, you don't worry about. But you all see how by replacing first n omega naught with omega and then replacing omega by 2 pi f, you get this. Now this is more common, the way you're actually going to take a look at this and talk about it. Y'all with me, class? Now we take a look at the spectrum of this. This is the bottom line. So please, this part, watch and make sure you get it down. When we plot the spectrum of this in the coast, and actually we're going to talk about these coefficients right here. when we use this C of n, and we talk about these coefficients, please just understand what I'm doing, why I'm doing it. And we look at that, I gotta first make sure you understand something about the sinc function itself. When I have sine x over x equal the sinc of x, right? That is the sinc of x. If you look at what that looks like versus x, for a sinc function, it has a value of 1, and it looks like this. And this first zero would be at x equal pi. Do y'all follow me on this, class? Now, if you talk about the argument x being much less than pi, really much less than 1 down here, then it's about 1. Y'all follow me? All right, but something starts happening when this value approaches really 1, and definitely it goes to 0 pi. Y'all follow me on that, class? It does. It's actually when that 1. So if we plot, and this is how, I want to make sure you understand, this is the sinc, what a sinc function looks like. Right here. And I'm going to go over here and plot this next part so you can appreciate it. I have time, thank God. So now, if we were to take a look at the spectrum of 2 magnitude C of n, here's how it's done. That's what we care about, because this, we're going to look at this spectrum versus frequency. We're going to do it this way. This will be the log of f right here in terms of the actual plot. I mean, the paper will take the log, so this would be like 1, 10, 100, 1,000, and so forth. You all follow me on this? It's a logarithmic axis on the horizontal axis. On the vertical axis, it would be 20 times the log. The reason it's 20 is C of n is proportional to the voltage. All right? If it was power, it would be C of n squared, then it would be 10, but it's always 20 times the log of the magnitude of, usually it's C of n, well, it'll be 2 C of n, because this is the coefficient of the cosine. So it's going to be 2 magnitude of C of n. But here's the thing you write down. Almost always on this axis, it will be dV microvolts. Now, I have to bring you up to speed. And I know you're taking a lot in right now, but you've had enough to understand it. You know, dB in general is what? For voltage, it's 20 times the log of the voltage. Do y'all remember that? If it's dB microvolts, that's 20 times the log of the magnitude of V over 10 to the minus 6. What it does is normalize or divides 10 to the minus 6 volts into voltage, so it gets dB microvolts. Do you all understand this? How many remember this kind of stuff? I've done this before in this class, I think, didn't I? Didn't I do dBm and dB? I think anytime you have dB anything, that anything is what you divide the quantity by. So if it's dBm, this would be a 10 because it would be power. 10 log of the power divided by 10 to the minus third. dB microvolts would be 20 log of voltage divided by 10 to the minus 6. It would be dB microvolts. So we divide this by 10 to the minus 6. That's the way it's done. Write this down. So when we do that for this thing right here, we get 20 times the log of it. This is going to be 2 times A times T over tau times the sinc of pi tau rise f times the sinc of pi tau f. Here's what happens. And this, please write down. This doesn't matter with these what the scale is on there, it's a log plot. What you'll always start out with is this. This will be flat. It will be 20 times the log of the magnitude of this first part. Remember, if you take log A times B, it's log A plus log B. So we're going to take a log of this, but that first part will be 20 times the log of 2A times the duty cycle divided by 10 to the minus 6. Do y'all follow me? That's just the log of this part right there. And then it takes the magnitude of that divided by 10 to the minus 6 because it's dB microvolts. Follow me on this stuff? You'll see it'll make sense. It stays flat. It stays flat until you hit the point where the first pole is, or when it starts coming down. Now, I didn't get to say this, but when you take a look at the sinc X, up close it's about 1, right? And the arguments of the sinc are about 0, it's about 1. But as you get to large values, if you talk about the envelope of the sinc function, if this is X and this is sinc of X, or sine of X over X, then it does this. And the shape of this is limited by 1 over X. Do y'all see that? Can you follow me on that? It's really going to be, yeah, it'll have that oscillation, but the limiting tips will always be given by 1 over X as X gets large. So what that means over here is, when you take the second part, the log of this term right here, it's 1 until this argument becomes about 1. Y'all follow me? When it becomes 1, all of a sudden it's like a Bode plot. It starts going down at 20 dB per decade at 1 over that. So write this down. The first break frequency right here will be at 1 over pi times tau. And this is the low frequency break. Remember, this is going to be an F. This is going to be F low here. It's not exactly like, before that was what? 1 over 2 pi RC for an RC circuit, right? Do you all remember that? Here it's different. It's 1 over pi tau. And it's when this term right here equals 1. So if you put F tau pi equals 1, you'll get F as 1 over pi tau. I don't like to dwell on that too much, but that's how you get it. When that goes to 1, that's when the dB starts breaking. And it'll break at a rate of 20 dB per decade. That's the reason the Bode plots are so important to understand. With me, class? Actually, at 20 dB, I've got that slanted a little heavy. Let me put it like this. Now, it keeps breaking at that frequency until you hit the high frequency breakpoint right here. And this is when pi tau rise F equals 1, or F is 1 over pi tau rise. Do you all see that, class? And then, once you hit that frequency, this is 1 over pi. Please write this down. You're going to need this information. This is F high. After that point, it starts breaking at minus 40 dB per decade. So far, so good? I'm going to give you something exact in a second. Are you with me, class? And I know it's a lot. I mean, the mathematics usually, because you haven't had this over and over again, it's a little daunting, but trust me, this stuff works and it's used all the time in what you do. So that's the Bode plot of that trapezoidal wave way back when that is used all the time, where you have this kind of a deal, right? It just repeats, where there's T, there's a tau, and there's a tau rise, and this is A. That's the spectrum of that. And this is so important. All right, so the next logical question is, so what? What are we going to do with it? And here's what happens. This is the part that's going to make sense to you, hopefully. Because now you're going to see this stuff in action. All right? So I have this waveform right here. And I say that the actual value of t, or I should say the fundamental frequency is 5 megahertz. So that means t is 1 over 5 megahertz. Okay? Then I'm going to say the value of this peak here, A, is 5 volts. Fair enough? Y'all with me? I'm giving you specific values. I gave you the magnitude is 5. I gave you the fundamental frequency is 5 megahertz, or t is 1 over 5 megahertz. Make sense to everybody? Then I'm going to give you the rise time. By the way, what is 1 over 5 megahertz? That's what? 0.2 times 10 to the minus 6 seconds, or it's 2 times 10 to the minus 7 seconds, right? Right? It's 200 nanoseconds, right? 200 nanoseconds. Correct, class? All right. Then I'm going to say that tau rise is equal to 20 nanoseconds. And I want the level. Here's the question. I want the level of the actual value of this signal. It's really going to be the envelope of the signal, but I want the value of the magnitude of the signal. This would be in dB microvolts at a certain frequency. So we're going to sketch this graph with the exact values. Then what we're going to do is I'll show you how to extrapolate the values anywhere here and here for the voltage in dB microvolts that would be there. Y'all with me? So follow me on this. First, we take a look at this. Here's the plot that's associated with that. First value I need is 20. If you have a calculator, get it. 20 times the log. That's a log base 10 of 2 times. By the way, I can give you duty cycles for this. So let me give you a duty time, or tau over t equals 0.5. So that's 50% of the time. With me, class? And, or duty cycle, I guess you use my duty time, as 0.5. Then with that said, I'm going to say that now I know it's flat, it's DC here, and this value would be 20 times the log base 10 of 2 times 8. Well, if the duty cycle is 0.5, then the 2 and the 0.5 cancel. I get A over 10 to the minus 6, or simply 5 over 10 to the minus 6, that would be dB microvolts, would be right here. Y'all agree with that? With me, class? That's what it is. It's very straightforward to get. You can give me that. It's like 133.6, I think, or 136. I forgot exactly. What did you get? 134. Is it 134? So this is 134 dB microvolt. Now, the first break frequency here is 1 over pi tau. This is versus f, and this is a logarithmic plot. So when I look at that, f low would be 1 over pi, and then tau is what? Well, if t is 2 times 10 to the minus 7th, right, that's the period. That means tau, the on time, would be 50% of that, or it would be half that, or it would be 10 to the minus 7th. Do you all see that, class? Remember, this is t, 2 times 10 to the minus 7. Tau is simply equal to, or tau over t is 0.5, or tau would be equal to t divided by 2, or this would be 10 to the minus 7th, right? Can you give me that one too?
3.18 times 10 to the 6.
Is that right? Anybody?
Mm-hmm.
All right, so this is going to be 3.18 times 10 to the 6 hertz. Now, after that, the signal starts falling at 20 dB per decade. I'm going to show you where it falls to, though. We got to find 1 over pi tau rise here. And that's 1 over what? I gave you a rise time of 20 nanoseconds. So it's 1 over pi times 20 nanoseconds, or 2 times 10 to the minus 8. What's that frequency?
One 1.59 times 10 to the 6th.
10 to the 7.
Say, check that again. Is
I
that-
got 10 to the 7, 1.59 times 10.
Yeah, 15.7 megahertz, right? Is that right?
Yeah.
15. This frequency always has to be greater than that frequency, or something is way amiss. Right? You can't have them switch. So it's going to come down from here at minus 20 dB per decade until I hit here, and then it's going to come down at minus 40 dB per decade. Are you with me? Just hang on. Now, here's why I did that. Because this is, and I know I've thrown a lot at you. I'm very appreciative of the fact you're here and listening. But you have the tools to do this. Now I'm going to ask a specific question, and this is what happened. They're going to say, what is the level of the signal? They really mean in dB microvolts at a given frequency. And I'm going to pick a frequency and listen to it. I know if I'm at 15.7 megahertz, I'm right there. So what I want is the value of this, or I want the signal stream. And at F equals, if that's 15, let's do it at 35 megahertz, all right? So what I really want is the signal, what the signal strength is going to be in that envelope at that frequency. You got me on this, class, everybody? Here's how you do that part. Now this you haven't seen, I don't think, in any of your courses. I'm going to put it right here. Y'all agree it starts here, right? That's what it is. So you put down my V for F equals, what did I put down, 35 megahertz? You start with that value, 134, and it is dB microvolts, so I'm going to imply that. I'm just going to leave it at that. Now, here's the next thing. You know, from here to here, it's going down at a rate of 20 dB per decade. Please listen to this part. This is important. You all agree with that? So now you're going to say minus 20 times the log. Well, you got to figure out how many decades it went over. Then you put the upper frequency, so you put F high over F low. It's going down at that rate. Remember, it's dB per decade, right? So if it was 1 decade here, the log, I mean, if you think about this, if you went from 100, from 10 to 100, this would be what? 10. The log of 10 is 1, it would be just 20 dB, right? If it was 2 decades, it would be 40 dB. 3 decades, it would be 60. Do you all follow me on this? All right, now I'm at this point. But then from here to here, it's at 40 dB per decade. So now I subtract minus 40 times the log of the final frequency, whatever you want to call it, that would be F, which would be 35 megahertz, over F high. Right, I'm calling this my F high right here. This is F low. And you'll get it. Now for our particular problem, this V at F equals 35 megahertz would be 134 minus 20 times the log of the upper frequency, 15 over the lower. So it'd be 15.7 or 3.18. Minus 40 times the log here of the upper frequency, which is 35, over the lower frequency was 15.7. And what do you get for that? Because this is in essence EMC analysis and the spectral domain. but I'm showing you. I know there's a lot of math that you have to kind of swallow to get there, but this is how it's really done.
106.
106, and that's 106 dB microvolts. And that is the one thing I wanted to conclude with today. I'm going to give you some problems. So the question is, are we going to have a quiz on this on Friday? If I would have got a little further, I think I'm going to do it on Monday. I'm going to give you homework. Please do it. I'm going to warn you on this homework. Just warn you. If you got questions, you better come Friday, because on Monday you're going to get a quiz. Now, good luck. You're going to be able to take it, right? Yeah, all right. And have fun at Texas A&M. Hope it goes well. Anybody else go?